In this series of lectures, we'll start describing the solutions for a shock propagating away from a point explosion into interstellar gas. And these are the so-called BlastWave solutions. And these are most often applied to a supernova explosion, which are a critical part of the energy balance of galaxies. Supernovae deposit something like 10 to the 51 ergs of energy into interstellar gas in a period of only maybe 24 hours, a blink of an eye in astronomical timescales. And this serves to push gas around to redistribute it. It also deposits heavy metals into the gas, and it heats the interstellar gas. And so the entire ecosystem of galaxies is reliant on the energy deposited by supernovae. And yet, it's actually relatively easy to describe how these supernovae deposit their energy and how they evolve with time by working through, based off of what we know from shocks and a little bit about how objects expand, we can work through and describe the time variation of the radius of a supernova explosion, as well as information about the pressure and how that relates to the initial energy. So this is all called the BlastWave solutions, or alternatively, they're often referred to as the Sedolph-Taylor solutions. And I'll digress for a second into a little bit of history about the Sedolph-Taylor solutions because it's kind of interesting. These solutions were developed in the 1940s by two scientists working on opposite ends of the world, one in Russia, Sedolph, and one in the United States, Taylor. And they were solutions that were developed to explain how the explosion of a nuclear bomb would propagate through the Earth's atmosphere. So this was a blast wave. It was a single explosion, single instantaneous deposit of energy from a nuclear bomb, and how this would grow as it moved through the atmosphere. And you can imagine these were fairly important solutions to make because they wanted to know whether, of course, an explosion would cover the entire atmosphere or whether it would be contained in time. But the other interesting thing about this is that neither of the teams knew about each other's work because it was fully classified. So Sedolph published his paper in Russian, I believe, in 1946. And because Taylor's work was classified by the US military, it wasn't able to be published until after the war and was published in 1952. And shortly afterwards, it was realized that both works had been developed pretty much simultaneously on opposite sides of the planet, and they were brought together and referred to as the Sedolph-Taylor solutions. And we now apply those same solutions as a simplified form of describing a supernova explosion in the interstellar gas, which is quite different, obviously, than Earth, but in fact, the physics are much the same. So over the next couple of lectures, we'll develop these Sedolph-Taylor solutions so that by the end, you have the ability to describe an instantaneous injection of energy into interstellar gas and how that propagates with time. And that will be our final bit of our fluids course.